Welcome to Chapter 6, where we explore exponential and logarithmic functions. In this introductory section, we will be exploring in our first part here the exponential side of things. So we'll take a look at exponential functions in this video. Now, we have been dealing a lot with polynomial functions, which is like x squared, 2x, things like that. In this case, with an exponential function, the x is no longer a base, but it's the exponent. So it's a little bit different. Exponential functions look like 2 to the x or 1/3 to the x. So an exponential function is a function of the form f of x equals b to the x. Now b does have some restrictions. B does have to be positive. Be positive. Because if it wasn't, we would be all over the place. Raising a negative number to an even or odd power would completely disrupt what this would look like. So b does have to be positive, and also b cannot be 1. Let's think about why that is. What's 1 to any power? 1. So that would just be a horizontal line, technically a function, but not an exponential one. It's just the line y equals 1. So an exponential function is of the form f of x equals b to the x, where b is our base and x is the exponent. B does have to be positive, but it cannot be 1. The first exponential function that we'll take a look at is 2 to the x. And it's funny that when I set this up, looking at your textbook, they made a comment in there about how it's always the first exponential function that a textbook explores. Let's think about probably why that is. I think it's because that exponential functions literally increase exponentially, and that's something we hear in everyday life when something gets super big, super fast. If we were to raise even just 3 to the x, 3 squared's already 9, and 3 to the third's already 27. We don't have a whole lot of room to graph that stuff on a normal graph when teaching this. So I think that's why 2 to the x is such a popular function to start with for exponential functions. Anyway, let's take a look at making a t-chart. And in making this t-chart, I'm actually going to make 3 columns. And you don't have to do all these columns, but I do want to just show the work behind what we're doing so you completely understand how to raise a number to even like a negative exponent. So I want to plug in the value -3 first, and this middle column will just be our work in here. So if we plug in -3, we're taking 2 to the -3rd. Recall that a negative exponent means it's going to end up in the opposite part of the fraction and become positive. So this is really 1/2 cubed, and 2 to the third, or 2 cubed, is 8. So our f of x ends up being 1/8. Let's try -2. If we plug -2 in, we'll have 2 to the -2nd, and that really means 1/2 squared, which is 1/4. So note that raising an integer here to a negative doesn't output a negative, right? We didn't get -8 and -4. Instead, we got 1/8 and 1/4. Then if we want to raise 2 to the -1st, we'll have 1/2 to the first, which is just 1/2. Next, let's raise our value to the 0. Anything to the 0 power is 1. So 2 to the 0 is 1. There's not really a lot of work there. That's just something that we have to remember. Next, I want to raise to the positive. We'll just do these ones real quickly. These are easier. 1, 2, and 3. So this is 2 to the first. That's just 2. There's not really a whole lot of work to be shown for these. 2 squared is 4, and 2 cubed is 8. So we have these multiple points that we can graph. So I'm going to do that real quick and then replay the video. All right, so I was able to graph this. I'm actually pretty proud of how it turned out. This is not the easiest thing to do with this program here. But we can see that even 2 to the x increases so quickly. So let's think about kind of what's happening here. If we plugged in larger and larger x values, as x approaches positive infinity, our right end behavior, like if we look at our graph, goes to infinity. It's not bounded by anything on the right. As we plug in larger x values, our f of x increases literally exponentially to infinity. Now, if we plug in smaller and smaller x values, what do we notice happens? Well, let's say we plugged in -4, we get 1/16. If we plug in -5, we get 1/32, and so on. We'll always have a smaller and smaller fraction, but we're never going to hit 0. So as x approaches negative infinity, our function approaches 0. It gets very, very close, but never quite hits it. We get tinier and tinier fractions as we go to the left. Let's write that out. So we can see our right end behavior is written out here, and our left end behavior, what we just talked about, is written out here. Do we have a horizontal asymptote? Yes, we do. Our horizontal asymptote is actually the line y equals 0. Now, because this is not a rational function, we don't follow those same rules for horizontal asymptotes. Instead, we can just clearly see by plugging in numbers that either approach infinity or negative infinity and just thinking about what's happening, we can see if our graph does in fact have a horizontal asymptote. Now, a horizontal asymptote doesn't always have to be what's happening to the right. It can be what's happening to the left as well. So our horizontal asymptote here is actually the x-axis, the line y equals 0, because as x approaches one of the infinities, in this case negative infinity, it's what our function's approaching. There aren't rules necessarily for exponential functions finding the horizontal asymptote like there were for rational functions with n and m, the degrees of the numerator and denominator. Instead, like I just said, we do have to just sort of use more of an intuitive approach and plug in numbers either approaching infinity or negative infinity and seeing what our graph is approaching as a horizontal line. We can do that by either using a table, using kind of the logical way we used our table just a moment ago, or taking a look at the graph and visually seeing what's happening. Notice we're approaching the horizontal line y equals 0 as our graph goes to the left. Next, let's talk about the domain of this function. So our domain, what we can plug in for x, we're not bounded by anything. Our graph goes everywhere to the left and everywhere to the right. We can plug in any x value we want here. You know, x is not under a square root or in a denominator, so our domain is all reals. And then our range, what comes out, we saw that no matter what we plugged in for x, positive, 0, or negative, we always got a certain type of y value out, and that was positive. So we're never going to hit 0. And we're always going to be positive. So our range is open 0 to infinity. The last thing I want to take a look at is this function increasing or decreasing? Remember, as we look from left to right, we can see like that's how we determine what our function is doing, increasing or decreasing. We read our function like we read a sentence left to right. And we can see that this function here is always increasing. Here it's increasing very slowly. 1/8 to 1/4 to 1/2 to 1, and then it starts increasing much more quickly. But it is increasing for all x. So we would write increasing, and we write these as x values. So it's increasing for all x from x is negative infinity to positive infinity, and we would say that it's decreasing nowhere. What about if we flip the script here and instead of raising 2 to the x, we raised 1/2 to the x? You know, an exponential function has a base that just has to be positive and not 1. So we can totally raise 1/2 to the x, and that's still an exponential function. Let's do the same thing here with a t-chart with 3 columns. Once again, the first number I want to plug in for x is -3. So when we plug in -3, we're taking 1/2 to the -3rd. Now there's a couple different ways to look at this. We can raise the 1 to the -3rd and the 2 to the -3rd, and then we'd have to flip both of them. Or, because it's a fraction raised to a negative, you can just flip them both. So this is really the reciprocal of 1/2, flipping it, which is 2 over 1, or just 2, and then you raise it to the positive third because that's how negative exponents work. And we're doing that with the fraction kind of with both the numerator and denominator at once by flipping it. So this is really 2 to the positive third. So it's 2 to the third over 1 to the third. 1 to the third is just 1. So this is really just 8. So our output is 8 here. Let's plug in -2. If we plug in -2, that means we're taking 1/2 to the -2nd. And that means we're flipping it because it's a negative exponent, and we're raising it to the positive second. So this is really 2 squared over 1 squared, which is 4 over 1, which is just 4. Okay, I fast forwarded just a little bit here, so I plugged in -1, used that same logic. Plugging in 0, any number to the 0 power is 1. Then plugging in 1, raising something to the first power, is just itself. How about if we plug in 2? That is 1/2 to the second, which really means 1 to the second over 2 to the second. So it's 1 over 2 squared. This is really 1 squared, which is just 1. So we get 1 to the 4th. 1 to the 4th. 1/4 is what I meant to say. And then if we plug in 3, which will be the last one that I plug in, we're taking 1/2 and raising it to the third power, which is 1 cubed over 2 cubed, which is 1/8. So a lot of the same outputs, except they're just swapped. And that's why I decided to do 1/2 to the x next, so you can see. So next I'll put this on our graph. So I graphed this one and took away the xy chart so we could analyze it a little bit. We can see that it's very similar to 2 to the x, except it's just flipped. We'll take a look at that relationship in a second here. Let's take a look at a couple of the characteristics of this graph. So our right end behavior, as x approaches positive infinity, what's happening to our function? Well, as we plug in larger and larger numbers, like if we plugged in 4, we'd have 1/16. If we plugged in 5, we'd have 1/32. If we plugged in 6, 1 over 64, and so on. We're getting smaller and smaller fractions approaching 0. So our function, the right end behavior, goes to 0. And in your textbook, they do 0 to this little positive number because we're approaching 0 from up top. However, that's not something that I'm as familiar with or sees as necessary in the mathematical notation side of this. So just saying approaches 0 is completely fine. But just so you know, your textbook does that to show that you're approaching 0 from the top. Then our left end behavior, as x approaches negative infinity, our function goes to infinity. If we plug in smaller and smaller numbers, like when we plugged in, if we plug in -4, we'll get 16. If we plug in -5, we'll get 32, and so on. Our horizontal asymptote here is actually the same. Remember, the horizontal asymptote is what our graph approaches, like what horizontal line our graph approaches, either to the right or to the left. So in this case, our horizontal asymptote is also the x-axis, the line y equals 0, because our function approaches that to the right. Our domain, once again, is all reals, so I'll write that in a cooler way this time, all real numbers. Our range is once again from 0 open to infinity, because we never quite touch 0. Now this time, our graph is never increasing, but our graph is actually decreasing everywhere, because as we look at our graph from left to right, the y values are going down. This is pretty cool. Here's the relationship between 2 to the x and 1/2 to the x. They're actually a reflection about the y-axis, and the reason for that is because we can write 2 to the x, well, we can actually write 1/2 to the x as 2 to the -1st to the x, because 2 to the -1st is 1/2, and using properties of exponents, we can multiply these two together, and it's really 2 to the -x, which means a reflection about the y. So that's actually pretty cool. This is why this works. Anyway, you don't need to really understand all that right there, but I just wanted to show the relationship between a number to the x and then its reciprocal to the x. Note the similarities. They have the same y-intercept, the same horizontal asymptote, and I just think it looks cool. This is directly from your book. This is putting kind of everything that we just talked about into like one nice spot, all these properties. So we already saw the domain is all reals and our range for any b to the x. The y-intercept is 1. And y equals 0 is our horizontal asymptote. It is 1 to 1. Continuous and smooth. Continuous is more of a calculus idea, but I believe we have mentioned it this year. That just means that we have no like gaps, holes, or jumps or vertical asymptotes in the graph. And it's smooth, meaning it doesn't have any like sharp corners. Then we talked about this idea with increasing end behavior and what the graph looks like for when b was greater than 1, when we did like 2 to the x, and then when b was a fraction less than 1, like 1/2 to the x. So this is just a nice thing to have in your notes, or if you feel like you understand it, completely fine to not write down. Let's take a look at actually like applying these exponential functions. So exponential growth and decay is a huge idea that you'll see a lot in math, and we will definitely be exploring. But it doesn't always have to be like for some chemical byproduct or something like that. It can just be for anything. So if you buy a car, a brand new car, the moment you drive it off the lot, it actually loses a lot of value. So any car over time is obviously going to decrease in value. So if we note, we have this exponential function here that models the car's value based on its age in years, x. And we can see that since our b value is less than 1, it's 4/5, that means that it's going to be like a decay over time. It's going to go down. So the first thing we want to do is find and interpret v of 0. So let's plug 0 into our function. And this 25 out front will just be multiplied by whatever we get. So it's 4/5 and then to the 0. Anything to the 0 power is 1. So this is 25 times 1 or 25. That obviously doesn't mean the car's value is 25. Be careful, it's in thousands of dollars. So this means that when the car is 0 years old, so when the car is first manufactured, it's worth $25K. So there is one of many ways to write out this interpretation of v of 0. Then we want to find and interpret the horizontal asymptote. There's a couple different ways to do this. You can definitely take a look at Desmos, which we will do. You can also plug in larger and larger values to see what the asymptote is. First thing that we want to know is this an increasing exponential function or a decreasing one? Because b is less than 1, it's going to be decreasing and overall have this general shape going down from left to right. Because b is 4/5, it's between 0 and 1. So we know that as x gets larger and larger, we're going to be approaching our horizontal asymptote. So we can plug in larger and larger values and see what we end up getting. We can do all of this in Desmos. I put in our function, and I also messed with the settings here in order to get the best view. We know that we obviously can't have negative years, and I just went to 25 years since that made sense for a car. And then for the y-axis, we know that we start off at 25K, so up to 25, so I just went up to 30, and I like to see a little bit beneath where I know we're going to be since we can't have a negative value, so I just went down to -5 so I could see the x-axis. So when we take a look, it looks like our horizontal asymptote is 0. Now it's not always going to be this way, just depending on if we have like plus or minus here afterwards. But just as a reminder, you can go up to this feature here to get a table. So if we click that and then click this little table function, you can plug in values. So we want to see what's happening as x gets very large. So we're going to plug in larger and larger values for x. So I'll plug in 10. And its worth is about, $2.5 grand there. Then we'll plug in 15, getting larger. The value has gone down significantly to $879. Then let's plug in 20 as we get larger and larger. It's decreasing even more. Let's plug in 25. So we can see that we're approaching 0. We're getting smaller and smaller. Just for fun, even though this doesn't really make sense for a car, I'm going to plug in a pretty big values just to show mathematically what's happening. So we can plug in like 100, and we can see how small we're getting as our y value. 10 to the -9th means we have to move this decimal 9 times to the left. So this is super small. Basically, we're approaching 0, which is what we thought in the first place. So if we take a look at our function and we go all the way out to the right, we're definitely approaching 0. So our horizontal asymptote is y equals 0. And this means that as x gets larger and larger, the y value approaches 0. What does that mean in the context of the problem? Well, our x value is the car's age. So as the car ages, or as the car gets older and older, or as the car gets very old, a lot of ways to say that, its value, or worth, approaches 0. Now, we don't have to say 0 thousands of dollars just because $0 is the same thing. The last problem that we'll look at here deals with Newton's law of cooling, which is kind of neat. So this is another like exponential, I hate to say decay, but exponential like decline problem basically, because we know that as we have coffee sitting out, it's going to decrease in temperature. So we have degrees Fahrenheit of our coffee measured T minutes after being served. And it's modeled by this equation here, and we see E. E is a super, super important mathematical concept. It is just a number. So just FYI, E is about 2.718. It does go on forever. So it's irrational, and it's called transcendental, and it's important in calculus too because it's its own derivative. We'll get there next year. But just know that E is about 2.7. We will explore E a lot more in depth later in this chapter, but for now, that's all you need to know. First thing we want to do is find and interpret T of 0. So T of 0 means plug 0 in. So when we plug 0 in, we'll have 70 plus E to the 0. And E, I forgot the 90. That's important. So 90 E to the 0. And E to the 0, since E is just 2.7 approximately, it's just 1. E to the 0 is just 1. So we'll have 70 plus 90 times 1. So 70 plus 90 is 160. So that means that right when the coffee is served, so 0 minutes after being served, its temperature is 160 degrees Fahrenheit. Another way you could say that is the initial temperature of the coffee is 160 degrees Fahrenheit. The next thing we want to do is find and interpret the horizontal asymptote. We'll do this in the same way by looking at Desmos. As I'm plugging in, I want to just make sure we all know how to use E on the Desmos screen. So you want to go down here as you're typing in. You're literally going to go to ABC because E is a number. It took me a second to figure this out. So we'll click ABC, and then you just click E. And then you go back to the 1, 2, 3 side of it. And then raise it, so hit the A to the B power. And we want to raise it to the negative 0.1x in this case. Now, because we're raising this to a negative 0.1, even though E is larger than 1, you'd think that it would be growth. However, it's decay because if we look at E to the negative 0.1, T or X, as I wrote it on here, this really means you could rewrite this like this. And this actually means 1 over E to the 0.1. Or you can break it down in a couple different ways. Either way, and then, that's raised to the x. Either way, the base ends up being less than 1. So it is actually a decay problem here. Also, you can figure that it's decay just by looking at it or understanding that coffee is going to cool down over time. As we take a look, we can see that the horizontal asymptote looks like it's 70 in here. But just to be sure, I'm going to take a look at the table function and plug in large values. This is time in minutes, so it doesn't make sense really to have negative here. So let's plug in some large values. Let's plug in 10 minutes after the coffee is served. So we plugged in 10, we have it still 103 degrees. I'm still not anywhere close to being where it levels out, so I need to plug in something larger. So we'll plug in 20. Still getting there. Let's plug in an even larger number, 30. We'll try 45. And then I'm going to plug in something pretty big. I'll plug in, let's do 100. And so we can see that we're approaching 70. If I want to plug in something even larger, I can try 150 and so on. So we can see that we're clearly approaching 70 as our x values get larger and larger. So 70 is our horizontal asymptote, and that just might mean that the room temperature is 70 degrees. Before I said it might mean that the room temperature is 70. It does mean that the room temperature is 70. So y equals 70 is our horizontal asymptote. And so over time, our coffee is going to approach 70 degrees. So over time, the temperature of the coffee will approach 70 degrees Fahrenheit. In this video, we took a look at exponential functions, talked about when they're increasing or decreasing, and then we took a look at 2 examples that used exponential functions and analyzed them. Thanks for watching.